Welcome back to this second half of this lecture on we are discussing localization of modules, and in the last half, in the later part, we have defined what is a complex and what is a exact complex. So now let us see some easy examples. So I would put them as examples. These examples will often be used in the theory of modules usually. So as usual, A is a ring and we consider all modules. So A modules and 0 denote the 0 module. This is the 0 module, 0 A module. That is the abelian group, underlying abelian group is a trivial group, and scalar multiplication is also trivial. So now suppose I have a exact sequence like this 0 V W. There are only 3 terms in this sequence and this is F, and V is a module, W is a module, and F is a module homomorphism. That I will not write, that is understood because we are looking at the category of A modules. So this is exact. Let us write down the condition now, if and only if. So we have to, there is only one stage here. It should be exact here. That means homology here should be 0. But what is the homology here? That is the kernel of this map F and modulo the image of this map 0. This is the 0 map. From 0 module to V, there is only 0 map possible. This is the 0 map. Everybody 0 goes to 0. So this is exact if and only if F is injective. Because homology 0 means here this is the kernel and the image is 0. So this is image of 0 which is 0. So kernel is 0 is equivalent to saying the sequence is exact, that means F is injective. Okay. Similarly, if I have V, W and 0 here, and suppose this may be G, when is this exact? This is exact if and only if. Now here exactness here, that means the kernel of this map, which is kernel of this map, this is a 0 map. So kernel is, everybody is in the kernel. So W is the kernel. So W equal to kernel of 0, and on the side that should be the image. So this should be the image of G. But this means G is surjective. Note that such a sequence is always a complex, because what is the composition? 0 composed with F is 0. So this is always complex. This is also always a complex because composition is 0. There are only 3 terms. Okay. So third one. Now I can combine both. So I will take this one with the 4 terms V, W and 0. Now this should be 0 map, this should be 0 map, and suppose this map is F. Then this is exact. Now there are 2 conditions. If and only if. Condition here is F is injective, and condition here means F is surjective, and F is surjective. So that means F is bijective. That means F is a module homomorphism, isomorphism. Okay, one more, fourth. Now I can combine in more terms. So 0, V prime, F prime, V, F double prime, V double prime and 0. So this must be 0 map, this must be 0 map. So now we will have condition here. So let us put it 1, condition here 2, and condition here 3. So what is this? Is exact if and only if. What is the condition 1? That is, this f prime is injective. F prime is injective. Condition 2, its exact here means kernel of this map equal to image of this map. So image of f prime equal to kernel of, why denote this by f double prime? I want to denote by f only. Kernel of f. And third one, here f is surjective. Such a exact sequence is called a short exact sequence. Such an exact sequence is called a short exact sequence. And when is it a complex? If it's a complex, this is okay, but we have to just assume this inclusion. Then it is a complex. Equality, then it is exact. So these are good examples. Now from one more example or two more we will do it. So particular case, this will be the particular case of the earlier this one. So fifth if you like, let f is a module homomorphism from the module A V to W. Sometimes the more notation and language you use, the more precisely you become. So V to W, this is the A model homomorphism F, and from here I want to get hold of exact sequence. So kernel of F to V to 0. This is obviously exact, and this image of F, this is also obviously surjective. So this map is F. So x going to f of x, and this is just a natural inclusion map. This iota is a natural inclusion map. So any element x that is mapped to x only. Now let us check whether this sequence is a complex. So I have to check that these compositions are 0. So this is 0, so I don't have to check this composition is 0. Similarly this is 0, I don't have to check this composition is 0. So only you have to check this iota compose f is 0. But if I take any x in V, now I have written it other way. So we have to check f compose iota is 0. That means for every x it should be 0. So let x be in the kernel of f, then iota of x, and then I have to apply f, but iota of f, x is x only, so this is f of x, but x is in the kernel, so it is 0. So therefore this is 0, so this is a complex. Not only complex, but it is exact sequence, because I have to check exactness here. That means the kernel of this map should be the image of this is itself. This is a natural inclusion, and the kernel of this map is precisely the kernel. So this is a short exact sequence. This one is a short exact sequence of A modules. So from a module homomorphism you can also you can also define a short exact sequence. So the one more example 6, if U is a submodule of V, a submodule of V, then we have this natural surjective map from V to the quotient of V by U, and this is obviously surjective. So that means this sequence is exact, and U is a submodule, so this is a natural inclusion. So its inclusion, therefore this is injective, and the exactness here is also clear, because what is the kernel of this? This is the canonical residue class module homomorphism. The kernel here precisely, the kernel of this map is precisely U. This is usually I denote by pi. And what is the inclusion? That the image of the inclusion image, this is also U. So that means it's exact here. So this is a short exact sequence. Of A modules. Alright, so these are the way to get short exact sequences from the module homomorphism as well as from a quotient model, from a submodule. Now why did I do all this? That is because I want to understand this functor S inverse A more. So the S inverse A, this is from A modules, the category of A modules, to the category of S inverse A modules. S inverse A mod. We have associated to V, S inverse V, and to module homomorphism W, F, we have associated S inverse of F. And this is S inverse A module homomorphism. This is A module homomorphism. And we want to understand this more. So in this situation I will prove that the exact sequences are mapped onto exact sequences. That means this S inverse A is an exact functor. So we will prove that S inverse A is an exact functor. What does that mean? That is, S inverse maps exact sequences to exact sequences. So more precisely, we will prove the following proposition or theorem. So theorem, so as usual notation, A is a ring, S is a multiplicatively closed subset in A, and V W, okay, I will use, so I will use the next line. So V prime, V double prime, A modules, and V prime to V to V double prime, this is F, this is F prime, is or B an exact sequence of A modules and A module homomorphisms. That is, the exactness here only, that is image equal to kernel, image of F prime equal to kernel of F. Then when I apply S inverse, I get an exact sequence of S inverse A modules and S inverse A module homomorphism. So let us write then S inverse V prime to S inverse V to S inverse V double prime, this is S inverse of F and this is S inverse of F prime, is an exact sequence of S inverse A modules and S inverse A module homomorphisms. Proof: we only need to check that exactness here, because we already know it's anyway it's a complex is obvious. Complex is obvious because we know that S inverse of F compose F prime is same as S inverse F compose S inverse of F prime. So if this was 0, S inverse of that will also be 0, and that is this composition is 0. That simply means this is a complex, but we want to check more. So it's enough to check that the exactness here, that means image of this equal to kernel of this. So image of S inverse of F prime equal to kernel of S inverse of F. This is what we need to check. And because it is a complex already, we know this is contained here. This is clear. This is follows from this condition, because if I have somebody in the image of S inverse of F prime, that is an evaluate there. So it is, that means this inclusion is clear. So essentially we need to check. So only enough to prove that kernel of S inverse of F is contained in image of S inverse of F prime. This is what we need to check. So that is very easy to check. We only will take an element here and check it is there. Alright. So take an element here. So how does an element look like? That is an element here. So it will look like some x divided by s. This is in the kernel. So suppose that this is in the kernel. So where this x is in V and s is in S. And what is the meaning of the kernel? That is, so then S inverse of F on x by S is 0. But what is this by definition? This by definition apply f to the numerator, f of x divided by s. This is 0, and this is 0 where? In this modulus inverse of v double prime. And when do this is 0 in S inverse of some module? That means there is an element in S, so that kills the numerator, because this cross multiplication, this is 0. So this means there exists T in S such that T times Fx is 0. But T is in S and S is in A. So remember, this is a modulum of sum, so this is also equal to f of Tx. So f of Tx is 0. But that means what? So that means this Tx belongs to the kernel of f. But we know the original sequence is exact, so kernel equal to the image of the earlier one. So this is image of f prime. So that means this Tx is of the form f prime of x prime for some x prime in v prime. And what is that we want to prove? We want to prove that we started with an element here in kernel of S inverse f, and we want to prove that it is in the image of S inverse of f prime. So we have got hold of a candidate. So naturally we would like to check. So check that, we will check that this x by S equal to which one image? Now I have to take f prime of x prime and maybe this t. So I am just writing this, we will modify this. Alright, so if we have to check this equality, what will I have to check? Tx equal to this, right? When will this be equal? When will this be equal? That means I am just analyzing and then we will fix it up. So this is Tx minus or equal to S f prime x prime and multiplied by some other element. So S prime S prime. So there exists S prime in S with this, then only this equality will be there. So we are looking for such a equation, but we know Tx equal to this. So and this S prime, what can I take S prime and S? S is given to you. So you multiply this, if I multiply this by S on both sides, then what would I get? If I multiply this on both sides, alright. So let me write the result. So that is T, so I have given this, so Tx by St or Ts. This one is same thing as x by S, and this is equal to f prime of x prime by St. Let us check this now. So this is what by definition? This is f prime x prime divided by St. This is also S. So remember, we want to check this equality. This is clear because I can cancel t numerator denominator, and this is also clear by definition, and we want to therefore check this equal to this, but that is because that is equivalent to checking this first and last are equal, that is equivalent to checking St T x equal to S f prime x prime. But we have given this. So, this is we have given this, So, if I multiply both sides by this given S, so this will give us this and this will give us, all these are equal, and therefore, we would have checked this. This would be checked. So, that proves that we have an equality here. See, x by s, we found an element here given this x by s, we found that x by x equal to f prime x prime divided by st. This we found this equation. This is precisely the proof here. So, we did not check this, but we checked this one. So, this is what we have checked. So, that proves what we wanted to prove, equality here. Equality here we proved, and that proved the exactness of the sequence of S inverse A modules. Now, I want to deduce some consequences from here. Okay, let me write one corollary. Let U be a submodule of the module V. This is submodule of the A module V, and as usual our ring is fixed and a multiplicatively closed set is fixed. Then S inverse U is an S inverse A submodule of S inverse V, and the residue class S inverse A module S inverse V by S inverse U is isomorphic to the S inverse A module S inverse of V by U. That means what? That means the operations S inverse and going modulo, they commute. So, what I have written in words here, I will write in symbol, that is S inverse V modulo S inverse U. This is isomorphic to S inverse of V by U. So, whether I go modulo U first and then apply S inverse, or go modulo S inverse U first and then take the residue, then take the first apply the S inverse to the module and then take the residue. See, these are same. This is very important operation. So, let us prove. This is very simple. All right. So, this follows from the exact sequence. So, we have this U is a submodule of E. So, we have 0, U, V and V by U. This is exact sequence of A modules. Therefore, we get 0 S inverse u, S inverse of v, to S inverse of v by u to 0. This is the exact sequence of S inverse A modules. This is the pi residue class map, this is inclusion map, then this is S inverse of pi, and this is S inverse of inclusion map. And this is exact means, this is exact means, exactness here. So, exactness here, exactness here, and exactness here. This means this map is injective. So, this is injective, this is surjective, this is surjective. That means exactness here. And exactness here means the image equal to the kernel. So, anyway, this map is surjective, and what is the kernel of this map is precisely the image of this, which is S inverse u. So, by isomorphism theorem, S inverse of v modulo the image of this, which is the kernel of this, which is S inverse of u, then it will induce a map here, and this is the map is induced by S inverse of pi, and this is an isomorphism. I would just say by isomorphism theorem. All right. So, the typical situation will also come when you apply to the ring and ideal. So, let us just note that. So, note that if A is an ideal in the ring A, then S inverse of the ring A modulo S inverse of this ideal A, that will be isomorphic to S inverse of the residue class ring. This is a particular case of the earlier corollary. So, I will stop here. So, this isomorphism as isomorphism of rings. So, I will stop this second half now, and we will continue this for the next lecture. Little bit more properties of the modules and S inverse A. For example, what happens to the direct sums and what happens to the direct product and so on. Some little more I have to study this S inverse A, because this is so very important concept, and I will use it. After this, I will start understanding the basic topology on the spectrum of a commutative ring. So, thank you very much.